In our last lesson, we studied countable sets, specifically those sets that are finite or denumerable. We proved along the way that the Cartesian product of two copies of the integers is denumerable, and so is the set of rational numbers. That is also denumerable, hence countable. For today's lesson, we're going to go ahead and introduce some terminology at the start, namely the notion of what it means to be a cardinal number. And then we'll go further into properties of finite sets and then come back to countable sets at the end, which will allow us to start section 8.2 of the text. So let's go ahead and get started. So our first definition is as follows. Let us suppose that A is a finite set. Then there is a unique natural number n such that A is equinumerous to I sub n. Now this part over here, that there is a unique n, this is intuitive, but we have not proven it yet. And so one of the things that we are going to do today is prove that in fact we do have a unique natural number n such that A is equinumerous to I sub n. Well, when this is the case, we call that number n the cardinality of A, and denote it by using the absolute value symbol. And so whenever you see the symbol here, this is meant to be the cardinality of A. Another way of other authors would call this the order of A. So that's also another way of phrasing this. But for our purposes, I will continue to call it the cardinality of A. But what if A is infinite? How can we make sense of the cardinality of a set? And the answer comes with the notion of a cardinal number. And so this was a definition that was first introduced by Cantor. And so the cardinal number of a set A consists of all sets B such that B is equinumerous to A. Now, something about this definition is that it seems to be implying that a cardinal number is a set. Namely, a cardinal number is the set of all B's such that B is equinumerous to A. Now, that's how Cantor originally envisioned it, but that is not the case. And so this is an imprecise definition, and it has to make it rigorous does require us to talk about ordinal numbers, which I'll avoid, and so I'll say this in the spirit of the late 1800s. As we saw earlier in our course, Russell's paradox shows that there are sets that are not, that there are things that are not sets, and it's the same holds true with cardinal numbers. So cardinal numbers are not sets. But we're going to go ahead for now take our definition to be that this is a collection but not a set of all those sets that are equinumerous to the given set A. So let us continue, and I'll go ahead and give an example of something where it's infinite in just a moment to get a notion of how we're going to be working with cardinal numbers. So when A is a finite set, we are abusing notation, and we write that the cardinality of A is equal to n, where n is a natural number. And so whenever we say that the cardinality of A is equal to a natural number, it's understood that the set is finite, but just something to be cautious here is that we really are abusing notation in writing this. Because technically, the cardinal number for A is the collection of all B's such that B is equinumerous to A. And so we're looking at a universe of all sets where B also has the same number of elements as A. So continuing, in the case where A is denumerable, so that is, A is countable but not finite, then we say that the cardinality of A is equal to aleph naught, or aleph 0. So here is the Hebrew letter for aleph, and so this was the notation introduced by Cantor. And so that's our first example of a cardinal number that corresponds to an infinite set. And the reason for writing it as aleph 0 is that last time we proved the following theorem. If A is a subset of the positive integers and is infinite, then A is denumerable. In other words, we have that aleph naught is the smallest cardinal number corresponding to an infinite set. And so this is the smallest possible infinity. And so brings up our notation for Aleph naught. But this raises a question. What is Aleph? Can we talk about Aleph 1, Aleph 2, Aleph 3? And so we're going to hold off on that conversation until the next video or next week, once we discuss more about uncountable sets. That is a topic that has rich history. But for now, the thing about cardinal numbers is that we now have a new set of objects when we talk about cardinal numbers. And anytime we have a new set of objects, we want to ask, what structure do they have? Can we add them? Can we multiply them? Can we put orders? Can we put in an equality, a relation amongst the cardinal numbers? And the answer is yes. We can put in a notion of less than. And so, for example, if alpha and beta are two cardinal numbers, we say that alpha is less than beta if for any set A in alpha, and so keep in mind, alpha is the collection of all sets that are equinumerous to each other. And so for any set A in alpha and any set B in beta, we say that A is less than alpha is less than beta if A has the same cardinality as a subset of B. But B does not have the same cardinality as a subset of A. We can also interpret this in terms of symbols. So alpha is less than beta is the same as saying for all A, for all B, where A, the cardinality is equal to alpha, the cardinality of B is equal to beta, and there exists some subset C of B such that C is equinumerous to A, and so let me just back up. So notice that this portion right here is this portion of the statement. A has cardinality alpha, B has cardinality beta. This portion right here is this sentence right here, that A has the same cardinality as a subset of B. And now we need the second portion, which is, but B does not have the same cardinality as a subset of A. And so for all D, such that D is a subset of A, we have that D is not equinumerous to B. And so that is the translation of what it means for two cardinal numbers, alpha and beta, to have the property that alpha is less than beta. And so that is how we can compare cardinal numbers. If you were to take a further course in logic, you would study cardinal numbers in further detail, studying properties like how does one add these. There's also a related notion of ordinal numbers, which is the precise way of defining cardinal numbers in logic. But we will not touch upon that topic for our course. But it's just something good to be aware of. So now that we have this definition, let's go ahead and define what it means for alpha to be less than or equal to beta, where alpha and beta are cardinal numbers. So alpha less than or equal to beta if alpha is less than beta, or alpha is equal to beta. And so in particular, if A is a finite set, we have that the cardinality of A is always going to be less than Aleph naught. And this leads to the following question, which Cantor posed. Let A be an uncountable set. How many cardinal numbers beta are there such that Aleph naught is less than beta, which is less than the cardinality of A? And so this is a question we're going to come back to in a future lesson, and this has a connection to what is known as the continuum hypothesis. And so we'll discuss that further in a future lesson. So now that we have introduced cardinal numbers, let us go ahead and consider the case of finite sets in further detail. Because in defining cardinal numbers, one of the things that we took for granted was an intuitive statement, namely, if A has a finite number of elements, say n, then the cardinality of A is exactly n, and that n is unique. We haven't proven that statement. But to prove it, we need to prove with exercise number 7. Suppose A and B are sets, and A is finite. We want to prove that A is equinumerous to B if and only if B is also finite and the cardinality of A is equal to the cardinality of B. Now, why must we prove things that are intuitive, such as this? And that's one of the running themes for this course. We have proven a number of results. Some of them were things that we already knew to be true from our preconceived notions in mathematics, the square root of 2 being irrational. Every number can be factored as a product of primes. But there are things that are not as clear-cut as we would expect at first glance. As an example, and this is just an aside, let us take the integers, and then I'm going to call this symbol here adjoin the square root of -5. Now, this is as a set, it's a set of odd numbers of the form a plus b times the square root of -5, where a and b are integers. It turns out that in a course in algebraic number theory, one can extend the notions of what it means to be prime, to have a factor. All these notions that we have for the integers carry over to this set. And so this is part of what is known as algebraic number theory. And so there is a notion of prime. In this set. As an example, 2, 3, and then 1 plus the square root of -5, and 1 minus the square root of -5 are primes in the integers adjoin the square root of -5. Now, we have a bit of a problem, because if we look at 2 times 3, this is equal to 6, which is also equal to the product of 1 plus the square root of -5, 1 minus the square root of -5. And so 6 has 2 different prime factorizations. And now this leads to the following observation. We have that 2 divides 6, which is equal to 1 plus the square root of -5, 1 minus the square root of -5, but 2 does not divide 1 plus the square root of -5, and 2 does not divide 1 minus the square root of -5. And that is crucial, because when it comes to things that seem obvious for the integers, that is based on our preconceived notions. So one illustration that is happening here behind the scenes is the following theorem, which is known as Euclid's lemma. And this is a result that may seem like it's an automatic thing to prove, but it actually is involved, and we're going to prove this towards the end of our course. And what it says is the following. So let P be a natural number, be a prime. If A and B are integers such that P divides the product of A times B, then P divides A, or P divides B. So for example, In our example with 6 is equal to 2 times 3, so that's our example for A is equal to 2, B is equal to 3. And we have that if a prime divides 6, then that prime has to divide one of the factors. So in the case of 6, 2 divides 6, which is 2 times 3, but we have that 2 divides 2. And so we see that Euclid's lemma holds. But proving this is not as easy as it may seem, because we need to adhere to the properties of the integers. Because as we just demonstrated with this example, for the integers adjoin the square root of -5, we have an instance where a prime in this new realm divides 6, namely 2, but 2 does not divide the factors of 6 when we write 6 in this way. And those are the things that are hidden behind the scenes. And that is one of the drives for structures and future math courses. We want to make sure that everything is foolproof, because there are things that we may take to be true based on our experience that may actually not hold in general, but rely on a specific property of where we are working with. And on a related note, this notion of prime factorization. So here we have 6 has 2 different prime factorizations. This led to a question of, given something like this, which is known as a ring of integers, are there at most finitely many possible factorizations? Could it be possible to have a number that has infinitely many factorizations? And this was one of the big open questions in the late 1800s in number theory. And it was finally answered in 1914 by Minkowski, who proved that if you go to some realm of numbers that looks like this, there will always be at most finitely many different factorizations for some given element. And so here we have 6, it has 2 different prime factorizations, and the quantity that allows you to know how many different factorizations there are is known as the class number. And so Minkowski proved that the class number was finite. But he did that in a very complicated manner. He introduced an area of mathematics known today as the geometry of numbers in order to prove this result. Several decades later, it was that result that made Minkowski famous was reproven using a basic property of sets known as the Pigeonhole Principle. And that is what we are going to prove in just a moment. The Pigeonhole Principle, at its core, it's rather, to use the word obvious in this case, it's intuitive. We expect it to be true. But its consequences in mathematics can be profound when used appropriately, because it can give you proofs for results that can be otherwise very difficult to prove, but when seen in a different light, the Pigeonhole Principle can come to the rescue and solve it. I hope that this example illustrates that we can have something that can seem as evident or true at a glance, yet inside the structure of the argument, we really need to invoke properties of the integers, because it's something that does not hold universally once we extend away from the integers, as we see with the integers adjoin the square root of -5. Similarly, in structures with finite sets, we want to go through and make sure that everything is on a solid foundation, no matter how evident it may seem that the result should be. And this brings us to exercise number 6 in the homework that you have. And this exercise is emphasizing this point that we do have this uniqueness for cardinality for finite sets. So for number 6, you want to prove that for all natural numbers n and m, it is the case that I sub n is equinumerous to I sub m, then n is equal to m. And building on that, you want to prove that if A is finite, there is exactly one natural number n such that I sub n is equinumerous to A. Once you have that proof, now the definition I gave earlier is now on a solid foundation, because we do have that to define the cardinality of a set A, that we do in fact have a unique natural number n such that A is equinumerous to I sub n. Without number 6, when we define cardinality, it's still open if it's possible to have that A is equinumerous to I sub n and some I sub m where n is not equal to m. But proving number 6 now tells us the n is unique. And that allows us to define cardinal numbers for finite sets. And so this will be an exercise for the homework on Monday. And now, building on this, we're going to go ahead and consider the following exercise, which tells us that if A and B are sets, and A is finite, we want to show that if A is equinumerous to B, that is equivalent to B also being finite, and the cardinality of A being equal to the cardinality of B. Now the proof will follow in the following way. So suppose A is finite, then there is a unique natural number n such that the cardinality of A is equal to n. So in particular, A is equinumerous to I sub n. So now let us go ahead and do the proof for the two directions. So let's suppose first that A is equinumerous to B. Then, by Theorem 813, so this is the one that tells us that equinumerosity behaves identically to an equivalence relation. So Theorem 813 tells us that B is equinumerous to I sub n, and thus the cardinality of A is equal to the cardinality of B, and B is finite. And that finishes it off for the four direction. For the converse, we suppose that B is finite, and the cardinality of A is equal to the cardinality of B. Since n is equal to the cardinality of A, which is equal to the cardinality of B, we deduce that B is equinumerous to I sub n, and thus B is equinumerous to A. By, once again, Theorem 813. And that finishes the proof. But the main thing here is that, yes, this is something that we expect to be true, but it still needs to be proven. And that's one of the aspects of mathematics as you go further on in courses. We will prove even the statements that seem as evident from a glance or just based on our previous experience. But we want to make away with that assumption of it being true by intuition, because there will be cases in your mathematical career where you're going to experience where things that appear to be true are not actually true in general. And so we want to have a proof for every single result and build everything from the ground up. And that's what we have been doing as part of our course. And so now we're doing that for the finite cases, the finite sets. So the next exercise we're going to prove is 8a. So I'll do 8a, and then for homework you'll do 8b. And so for 8a, we want to show that if n is a natural number, and a is a subset of I sub n, then a is finite, and the cardinality of a is less than or equal to n. And if a is not equal to I sub n, then the cardinality of a is strictly less than n. So we are going to prove this by induction. So for n, a natural number, let P of n be the statement if A is a subset of I sub n, then A is finite, and the cardinality of A is less than or equal to n. So moreover, if A does not equal I sub n, then the cardinality of A is strictly less than n. So now that's our statement for induction. We're going to go ahead and prove this. So we want to start at 0. For n equals 0, observe that A is a subset of I sub 0, which is the empty set, implies that A itself is the empty set, and thus the cardinality of A is equal to 0, which is what we wanted to show. Now for the moreover part, this aspect becomes vacuous, since A must be the empty set, and so this here will always hold true. So this shows that P of 0 is true. It's true. So for the inductive hypothesis, so now suppose P of n is true for some n. Now what we want to do is consider the case of n plus 1. So we're going to consider I sub n plus 1 and a subset A of I sub n plus 1. So next, let A be a subset of I sub n plus 1 if A is equal to I sub n plus 1. A is equinumerous to I sub n plus 1, and thus the cardinality of A is equal to n plus 1. Suppose instead that A was a proper subset of I sub n plus 1. So recall that this notation tells us that A is a subset, but it's not equal to I sub n plus 1. Then there is, so let's think this through. So if we are a proper subset of I sub n plus 1, but I sub n plus 1 is all the natural numbers going from 1, 2, 3, all the way through n plus 1. So if A is a subset but not equal, that means that there is some natural number k between 1 and n plus 1 that is not in A. And so then there is a k in I sub n plus 1 such that k is not in A. So now what we are going to do is construct a function that takes us from A to a subset of I sub n. Because the crucial thing here is that we need to be able to use the induction hypothesis. The induction hypothesis holds true for any set, any subset of I sub n. And so let's go ahead and do that. So let's go ahead and construct the following function. So let f be the function going from A to I sub n be defined by f of m, where this is going to be equal to m if m is less than k, and it will be equal to m minus 1 if m is greater than k. Now we claim that f is 1 to 1, so the way we do this, we have two options. We have to show f of A equals f of B implies that A is equal to B, or the contrapositive, A does not equal B implies that f of A does not equal f of B. So let us consider the case when A is not equal to B. So suppose m does not equal to some L, then without loss of generality, we may assume that m is strictly less than L. So we have two cases. The cases when m and L are both less than k. Actually, three cases. M less than L is less than k. M is less than k, less than L. And then finally, k is greater than both m and L. But now, I'm going to go ahead and put those two of those cases as one. So case one. Actually, do we proceed by cases? So case one, suppose that m less than L is less than k. Then f of m is going to be equal to m, which is not equal to f of L, which by definition is equal to L. And we know that m is not equal to L, so that finishes it out for that case. Case 2, suppose that k is less than m, which is less than L. Then, as before, we look at f of m. F of m is going to now be m minus 1. And this, of course, is not equal to f of L, which is now equal to L minus 1, which would in turn imply that m is equal to L. And that will be a contradiction. So we have this case here. And so now finally case 3. So now we're going to suppose that m is less than k, which is less than L. Then we have f of m is equal to m. And we have f of L is equal to L minus 1. Now, we want to prove f of a, that f of m does not equal f of L. So observe, L minus 1, by definition, is going to be greater than or equal to k, since we know that L is greater than k. So if we subtract 1, it will have to be greater than or equal to k. And thus, m is strictly less than L minus 1, since we know that m is strictly less than k. So in particular, f of m does not equal f of L, which shows that f is 1 to 1, since now we have exhausted all the three possibilities. So since f is 1 to 1, we have that f of a, the image of a under f, that is the collection of all those f of a's, a in A, is a subset of I sub n. And f of a is equinumerous to A. So keep in mind that this fact over here we have used before. If f is a 1-to-1 function, we can define a bijection. So namely, we can let g be the function going from f of a, from a to f of a, defined by g of a is equal to g of m, f of m. And so that will give us a bijective function, since now we have that, by definition, f of a, that's the range of f, which is the way we define g. And so that's where this fact is coming from, that f of a is equinumerous to a, that the cardinality is less than or equal to n. So by the induction hypothesis, we have f of a being a subset of I sub n implies that the cardinality of f of a is less than or equal to n. Therefore, the cardinality of a is less than or equal to n, which is what we wanted to show, since now less than or equal to n tells us that this is strictly less than n. Thus, a is less than n plus 1, which concludes the proof. Or I should say, which shows that p of n plus 1 is true. And therefore, that 8a holds by induction. And that finishes it off for 8a. But notice that the key ingredient is constructing this one-to-one function. So we constructed this function, we showed it was one-to-one, which allowed us to then use our induction hypothesis, because now we had a subset of I sub n. And whenever we have a subset of I sub n, since we are assuming by the inductive step that p of n is true, we get that f of a, the cardinality has to be less than or equal to n. But that's enough for what we want to prove, since we wanted to show in the case when a was not equal to I sub n plus 1, we wanted to show that the cardinality of a was strictly less than n plus 1. And so that finishes it off. And so this brings us to the famous Pigeonhole Principle, one of the most intuitive yet important statements of all of mathematics. And what the Pigeonhole Principle tells us is that if the cardinality of a is greater than the cardinality of b, there cannot be a one-to-one function between the two. So we can visualize this with a picture. So here's our set A. It has 5 elements, and here's our set B. It has 2 elements. If we had any function from A to B, we can never find a function that will be one-to-one, because once we have an element from A that maps to A, say 1, we have 1 mapping to A, then we can say 2 maps to B. 3, 4, 5 have to map to one of A or B, since f is a function. And so this function cannot be one-to-one. So the Pigeonhole Principle is very intuitive. And the proof of it is now essentially done by the previous 2 exercises we did. So to prove the Pigeonhole Principle, we go ahead and do the contrapositive. So we're going to prove the contrapositive of this. So we're going to do 11b. And for homework, you're going to do 11a and 11c. And so for this, so we prove the contrapositive. Namely, if f is one-to-one, then the cardinality of A is going to be less than or equal to the cardinality of B. Alright, so let's go ahead and show this. So now, f is one-to-one. Since f is one-to-one, g from A to f of A defined by g of lowercase a maps to f of lowercase a is a bijective function and thus a is equinumerous to f of a. Now since f of a is a subset of b, we have by exercise 8b that the cardinality of f of a is less than or equal to the cardinality of b. And so that was the second portion, the part that you'll prove for homework. So 8b, which tells us that if a is a finite set and b is a subset of a, then b is finite and the cardinality of b is less than or equal to the cardinality of a. So we have cardinality of f of a less than or equal to the cardinality of b, but now we have that a is equinumerous to f of a. And since, moreover, the cardinality of a is equal to the cardinality of f of a, since a is equinumerous to f of a, and hence we get the cardinality of a is less than or equal to the cardinality of b. And that's what we wanted to prove. And so we now have the proof of the pigeonhole principle. Now, the pigeonhole principle also has, as a consequence, non-mathematical consequences. So for this course, there are at least two people. So as a consequence, so there are at least two people in this class who have the same birthday. Here, of course, we're defining f to be people in the course maps to months in the year. And now we have f of the person is birthday equal to the birthday month of a. So in my case, f of Alex will equal October. And so that's one application of the pigeonhole principle away from the realm of mathematical consequences. Because now we have, since there are 12 months in the year, and there's more than 12 people in the course, we will end up getting that there must be at least two people who share the same birthday. This actually generalizes. And so we have the following generalization to the pigeonhole principle. So the generalization is as follows. If f is a function from a to b, the cardinality of a is equal to m, the cardinality of b is equal to n, and we have that m is greater than k times n for some positive integer k, then there is a b in b such that the inverse image of the set containing b, the cardinality of the inverse image, is at least k plus 1. So here recall that the inverse image is defined as the set of a's and a's such that f of a is equal to b. So this will be given as a exercise to prove later on. But for now, let's see a consequence of this if we continue to extend the notion of the birthday function for the course, but now extend it to everyone at Carleton. And so what we get is the following. So here's the generalized example. We're going to let A be the set of students at Carleton, and B be the collection of months / dates in a year. And so we're including leap year here. So the set B has 366. From Carleton's admissions office, we have that the set A has 2,046 students. And we're going to define our function f from a to b, defined as f of a goes to the month/date, where the month/date is the birthday of a. Now, the generalization of the pigeonhole principle now tells us that there are at least 6 students at Carleton that share the same birthday. And the reason for this is that if we take k to be 6 in the generalization, we have that k times the cardinality of n. So we have 5 for k. 5 times the cardinality of b, which is 366. This is equal to 1,830, which is of course less than the total students enrolled. And now we have that by the generalization there will be 5 plus 1 elements for some in the pre-image, in the inverse image of some b in the dates of the year. And so that's how we are applying the generalization of the pigeonhole principle in this example. Another consequence that is commonly used is that if we were to take everyone on Earth and have a function defined from that person to the number of hairs that person has, then there will be at least 2 people on the planet that have the same number of hairs. And so that's another application of the pigeonhole principle, where now to do that, we of course have to look at the average number of hairs that a human has. And so that's just another instance where we can use the pigeonhole principle to get these sort of deductions from everyday examples. So let's return to the text. So we're now going to prove Theorem 817. So here we have A and B are disjoint finite sets, and we want to prove that the union of A and B, the cardinality of the union, is equal to the cardinality of A plus the cardinality of B. And so let's prove this. So now we know that A and B are both finite sets. So since A and B are finite sets, there are unique natural numbers n and m such that A is equinumerous to I sub n and B is equinumerous to I sub m. So next, observe that I sub m is equinumerous to the set n plus 1, n plus 2, all the way to n plus m, since here we have that this set here, let's go ahead and call it C, since the cardinality of C is equal to m by construction. But now exercise 7 comes in, because exercise 7 tells us that if 2 sets are equinumerous, that is equivalent to the cardinalities of the 2 sets being equal. So with this exercise we get, so by exercise 8.1.7, we have that the cardinality of C is equal to the cardinality of B, which is of course m. Now we can use Theorem 812, which tells us that if A is equinumerous to B, C is equinumerous to D, and we know that A and C are disjoint, B and D are disjoint, then A union C is equinumerous to B union D. From here, the way that this applies to us is as follows. So note that C intersect I sub n is empty, And thus, Theorem 812 implies that A union B is equinumerous to I sub n, since A is equinumerous to I sub n, union C, since B is equinumerous to B, which is equal to, by construction, if we take the union of I sub n union C, that is I sub n plus m. Therefore, the cardinality of A union B is equal to n plus m, which is equal to the cardinality of A plus the cardinality of B. And that finishes it off for this proof. And so that concludes it for today's lesson. Our next lesson will go into countable sets, and so then we'll actually start 8.2, and so that will be the material for Wednesday, and then for this coming Monday is when we will first start to investigate infinite sets, specifically uncountable sets.